Okay, so last time we discussed differential kinematics. The motivation is that we want to see, given the joint velocities, we want to see how the end effector moves. With how much velocity does it move? And by velocity, I mean both, sorry, linear velocity and angular velocities. And then we, differential motion, what is differential motion? So remember your forward kinematics problem in which every joint goes through some angular motion. Let's call it theta, theta 1, theta 2, theta 3, and so on all the way to theta n, if there are n joints or n degrees of freedom. And they contribute to, each one of the thetas contribute to, sorry, a Cartesian velocity or a Cartesian position. Here by x you can say that it's the Cartesian position. I mean it's both xyz, or you can just say that it's just along x. That's okay. X of the tool frame. So let's say you have assigned a tool frame here. Okay. So let's say this is your base frame and that is your this is your Z naught. Okay. And this is your Y naught. And this is your X naught. Okay. So and then you assign a frame to the tool. So let's say it's right, normally it's assigned here. Okay. So we call this, let's say Z tool. And then this is Y. Y, Z, and Y is upward, and that is your, into the page, that is your X of the tool. Okay, so so now we want, when we say X, then by linear velocity we mean, let's say this is the origin of the tool frame. So this whole point, it will have G Samad. Any question?
Sir, the students का था सोच रहा mics off किया थे देर ज़्यादा शोर कर दी sir.
Okay.
Chat क्यों मुझे कल बावे चल.
Okay. It's okay. I'll mute all of them. Whoever wants to talk, he has to first raise his hand or just type in the chat. So I'll mute everyone. Sorry, not unmute, mute. Okay. So now it should be fine. So this is the point that which we're interested in. It's the velocity. So this is the origin. So when we say px, so px is the position of the origin of the end effector along x of the base. So along this axis, so you can see that it's here. It's a, so that is how it moves along x. And the rate of change of that position is the linear velocity along x. So if this position, we take its derivative with respect to time, this is give you the x component of the linear velocity of the end effector. Similarly, there is a y component which is in this current configuration. It's from here. So yeah, so this is your y. We say this is the position of the origin of the tool frame along y. Okay, but the arm will not always be in this configuration. It can move around. So p of the origin of along y also moves around. Okay, so but we are interested, and the derivative of that one will be our vy, and then there will be z. Z is how much you're along this z which is out of the page. Okay, so sometimes just think of the arm that it will start to coming towards you. Okay, and that will be z. And it's not that one velocity exists at a time and others are zero. No, there might be a velocity vector which is the which has these three components. These are Cartesian components, okay. These are linear velocities. Linear velocity. And similarly, if you look at how this frame changes its orientation about this x. For example, it was here, but in order to do a certain job, this frame rotated a little bit. So, or not a little bit. Let's say this rotated 90 degrees about the x of the base. Then this y will point towards you. Okay, and that x will then point upward, because now it's point into the page. And z will remain the same, because z is same as x naught. It's along x naught. So we assume that we are talking about. And let's say that change in theta about this, that 90 degrees change, if you divide that change in theta divided by the change in time, dt, that will give you omega x. And think about it's rotating continuously, then omega x is a constant value. Okay? And similarly, you might change your orientation about this y of the global frame. We call that omega y. Okay? Who will change orientation? Tool will change orientation. And similarly, the tool might change its orientation about the global z. And that's what we call this. Okay? So every time there is a change in orientation, so the tool frame will no more look like this. X, y, and z will change their direction, their orientation. So these are three linear velocities. Angular velocities. And that's why these are angular velocities. And normally we group them together. These 6 velocities, we group them as Vx, Vy, Vz, omega about x, omega about y, and omega about z. Okay, and this is 6 by 1 vector. We can find it from joint velocities. In this case, theta 1, joint 1, theta 2, all the way to theta n. And we call this Jacobian. This Jacobian is the function of this. It's not a constant value. The moment you change the configuration, the moment you change the values of these thetas, okay, there is a dot on it. Sorry, there's a dot on it. And the short version of this is v. When we say 1v, it means these 6. It's a vector, 6 by 1. It is just the Jacobian times q dot, and q dot is n by 1. There might be n joints in your arm. So, and this is 6 velocities, Cartesian velocities. I sometimes call this Cartesian velocities, sometimes I call this tool velocities, sometimes I call this end-effector velocities, but this is what I mean by these terms. And then this will be your 6 by n matrix. Okay, sorry. So by x here, you can take any p along x, or you can take all the 3, or you can take all the 3 linear positions and linear angular position. If there is any change in theta by a small amount as delta theta, there will be obviously the end effector will move by a certain amount of delta x. So there's a change in theta's values. Every joint is undergoing through some change in the angular position, or maybe linear position. And then there is the corresponding change at the Cartesian level, at the end effector level. If you divide this by delta t and divide this by delta t, then you will get linear and angular velocities. Okay. All right, so then last time we did this example, we took a very simple arm which just comprises of one joint, and that's linear joint. So we know that the only way for the Vx to be along, let's say your global frame is like this. This is your x naught and this is your y naught. Okay, and z is towards you. This is your z. So your v clearly is here is vx. Vy and vz are 0. Okay, or instead of giving it x, we can write it in a vector form as this. Vx will be not 0, Vy will be 0, and Vz will be 0. And then you have to write the the unit vector as well. And the unit vector here is k. The reason they call it k is we assumed previously that our joint variable will always be along z. So let's call this z. Okay. And that one is your x naught. Let's say this is our x naught. And this is our y naught. This is our y naught out of the page. Okay. So z naught, then this k is the unit vector. Sorry about that. This k is the unit vector along z naught, standard unit vector, which is 0, 0, 1. And now we'll not call this v along x. This will be 0, but we'll call it v along y. V along z. Okay. And when you do that, okay, when you do multiplication, let's say v is this, you normally put this 0, 0, vz, derivation, vz. Okay, so this will become your vz. Okay, so but generally, whatever this might be some other x's, but this is the unit vector. But conventionally, we'll always move along. Prismatic joint will always make it move along z. And there is no way that this q dot can affect the angular motion of the independent, because it's a prismatic joint, a linear joint. Okay. So a linear motion at the joint level can only contribute to the linear motion at the Cartesian level, at the end effector level. Okay, and an angular motion at the joint level can contribute both to the angular moment of the end effector and linear motion of the end effector, because whenever we go through an angular motion, okay, so whatever angular velocity this is going through, let's say this is 1 RPM, then the end effector will also move at 1 RPM. But angular motion always contribute to the linear motion, which because of this formula, the tangential velocity is the r times omega. Okay, this was not the case there. So here now, from the angular motion, q dot is angular motion. It's your omega. You are getting a linear part, and you are getting an angular part. K is the unit vector. It's the simplest one joint, just simple joint. Okay, prismatic, revolution. Okay, let's make these two together. And let's make a robotic arm which has two joints. One is a rotary joint, a revolute joint, undergoing through Q1 or Q1 dot. Its angular position, angular speed. Okay. So Q1 is our joint variable. In this case, it is θ1, and Q1 dot is our θ1 dot. And this one is our, let's say this is our D2, because it's a prismatic joint. The joint variable is distance, displacement, and Q dot is D2 dot. This is in radians, this is in meters. Okay. Okay, and then we went through this derivation last time, that the angular velocity, the linear velocity, the angular velocities, they're the function of both these joint positions. It depends where the arm is positioned. Okay. And we also have, it's also the function of angular velocities. Okay. So just give me a second, okay. Wait, or not now, after 8 minutes. When this session ends, then we'll start another one, okay? So then I'll take a 2-minute break. Okay, so these velocities, they're the function of q and q dot, okay? And then we further on went that function is actually, we can write it as, we can separate out all the joint velocities, okay? And we can separate out anything else and group it in a matrix form, write it in a matrix form, and we call that Jacobian. And then we went on to derive this Jacobian. So for derivation purposes, we split the Jacobian into two parts, the linear velocity part and the angular velocity part. So we can say that our J, for the sake of derivation, will have two parts, JV and JO. In some books, they call it JP and J omega. Okay? But there are, this is for the sake of derivation. And then this is also a matrix, smaller matrix than the J, but it has a certain number of rows, 3 number of rows, and n number of columns. N is the number of joints. So let's say you have 2 joints, then it will have two columns. Okay? Because J11 has to multiply with this, J12 has to multiply with this. So whatever the number of rows is here, those should be the number of columns there, otherwise multiplication is not possible. For multiplication to be possible, the number of columns in the product should be equal to the number of rows in the second. So that's how you decide the number of columns. And you decide the number of rows based on what is on the left side, okay? So right now we only have 2 rows because we know for sure that Z dot is always 0. There is no motion possible about the Z. So our base frame looks like this. Our base frame is Z is towards you, okay? So towards you is like this. And let's say this is our X naught. And G is towards you and Y is upward. Y naught. Okay? So, yeah, this is the joint figure. And for the second one, we can say that this is our Z1. Okay? And let's call, this is our Z1. Y1 can be upward. And X0 could be this. X1 could be into the field. So by convention, we make our joint move about Z0 if it is a revolute joint, or along Z if it is a linear joint. So here we are having motion about Z0, and here we are having motion along Z1, linear motion. Okay. So anyway, if you look here, the only rotational motion in the system is about a global Z. There is no Ji Farhat. Farhat, Ji. Farhat.
जी सर ये वाई नॉट की जगह वाई वन कर लो ये सेकेंड वाई नॉट है
Yes, good. Thank you. Let's go Y1.
Y1.
Okay, so now we know that this velocity can have a component. This velocity can have a component along X and component along Y. For example, in current vector form, if I were to find the 2 components of this velocity, this would be my Vx and that would be my Vy. And there is no way there could be a Z component because we cannot, the arm cannot come out. Rotary joint, so this arm will never make a motion towards you. It will always stay in the plane. Okay? So let's go and do the derivation. So we then last time said that we can find the Jacobian, the elements of the Jacobian matrix through partial differentiation. Because we know that any change in position at the end effector level, it is a function of all the Q's. It's a function of all the q's. And then the q's are further a function of time, because we know that every joint has a velocity. And that velocity is q dot. q1 dot in the first joint case, q2 dot in the second joint case. So this is the formula to find the x component, x dot, or we also called it Vx previously. Okay, partial differentiation, partial differential of the position of the end effector with respect to q1 plus q2, and then I explained the partial, how to take partial derivative. Let's say z is a function of x, x is the independent variable, z is the dependent variable, and let's say the function takes the form x squared plus 1. It could be any form, but let's say it's x squared plus 1. And we further know that x further is a function of time. Then if you are to find the derivative of z with respect to x, then this is how you find it. It would be just 2x. The derivative of x squared is 2x, derivative of 1 is 0. So you'll get 2x. But if you know that x is further a function of time, then you better call this as dz derivative of z with respect to time. You will take in two steps. First, differentiate z with respect to x, because z depends on x, and then differentiate x with respect to time. Then only then you will get z dot. Okay, so what I mean to say is you first differentiate this with respect to x, you will get 2x, but you further differentiate this with respect to time. Okay, so you will get this. If you had a multivariable function where z was a function of two variables, x and y, okay, and if they were x and y were not further functions of time, then we would just do partial of z with respect to x, because it partially depends on x. Sorry, plus partial of z with respect to y. We will first take the function differentiated with respect to x. While we do that, we treat y as constant. That's why the derivative of this with respect to partial derivative of this with respect to x is just 2x, because this is constant. The derivative of this with respect to x is 0. This is constant. And then we take the z function again, and this time we take the partial with respect to y. Okay? एक मिनट अच्छा, इससे पहले ये मीटिंग ख़त्म हो जाए, मैं इस रिकॉर्डिंग को स्टॉप कर लूँ कि ये प्रॉपर तरीके से इसको सेव कर लें. I don't want to lose it. I'll resume in a minute. Okay, so these were the basics of how to differentiate a function, a multivariable function, where the independent variables are further, they are functions of time. So you are having a function of something which is again a function of time. It's a composite function we get. So we, in order to find the dz by dt, you have to go in these steps. You know that z not only depends on x, it also depends on y. So you will take the partial differential of z with respect to x, and further the derivative of x with respect to time, plus partial of z with respect to y into derivative of y with respect to time. Plus, if there is further variables, and then you will keep on adding. Okay, so that we need to do for our Jacobian as well. Okay, so let's do an example that will practice us using this formula. So let's say, yeah. So, and then we take these guys, q1 dot outside, we group it separate in a separate vector, and we take this q dot here. Okay, so this q dot is your, this is here, and this q1 dot is here, and the rest that you see in red, they are the elements of the Jacobian matrix. So that's all we need to find. So let's do an example here. Let's see if we have this 2 degrees of freedom arm, where this is well not a link. It just it's just showing that z naught is out of the page. Z naught is out of the page. Okay. Good. it's towards you. That's the only purpose of this link. Otherwise, the link is here, uh, from origin 0 to origin 1, and then to the origin of the 2. So this is your arm. Okay. And then the forward kinematics are extremely simple. It's just like you're moving in a circle. So in order to find the Cartesian coordinates of this, what you do is you just take this theta, and you take the hypotenuse, and then you x is the r cosine of this theta, and y is the r sine of this theta. In this case, instead of r, we have q2. This is distance, the joint variable of joint 2. And then instead of theta, we have q1. Okay, so this formula will become x is r cos theta. We'll write q2 cos of q1, and y is r sine theta. We'll write q2 sine of q1, and z is 0. There is no change in the position of the z of the end effector. There is no change in position of the end effector along z naught. Okay, and then we take partials of this. We take this x, we take its partial with respect to q1, and that's how we do here. Take the x, it's q2 cos of q1, and take with respect to q1. So treat q2 constant. So this will come as it is. And instead of cos of q1, we'll get minus sine q1. And then, of course, you have to take further the derivative of q1 with respect to time. We'll wait. Acha ji. So we took partials, and then we get this. And then take the partial of Vx with respect to q2, and this time treat q1 as constant. So if you treat q1 as constant, then cos of q1 is also constant, and it will come as it is. Okay, and the partial of q2 with respect to q2 will just give you 1. So there is no coefficient. The coefficient is 1 here. And d of q2 with respect to time will become q2 dot. So you continue doing this. So this is this element of the Jacobian. Let's call it J11, first row, first column. J12 is cos of q1. J21 is take the partial of the y now with respect to q1. So treat q2 as constant, and sine of q1, the partial of this, the partial derivative of this is cos of q1. Okay? Yeah. And the second row and second column, the last element of the Jacobian, it will be take the partial of this with respect to q2. And it's the same. So sine, as q1 is being treated constant in this expression, then sine of q1 is also constant. It will come as it is. And partial of q2 with respect to q2 will give you 1. Okay. So now your Jacobian is complete. If we bring up, we bring all the elements together, so this is how it will look like. And you can see that this is just the linear part of the Jacobian. So we're going to find the angular part next. Okay. And now you see that this J matrix is a function of q1 and q2. We see q1 and q2 both variables there in the matrix. The moment you vary them, the numerical values, the resulting numerical values will change. So it's not a constant matrix, as I said earlier. It depends on which pose your arm is in. For example, let's take q1 0. It looks like 0 because it looks, okay, so z naught is here and z1 is here. Let's say your theta 1, let's call it q1. Q1 is 0, and let's say your D2 is, Q2 is half meters, and that is in radians. So your Jacobian, the velocity part of the Jacobian will be minus Q2 sine of Q1, so sine of 0 is 0, cos of Q1 will be 1, and Q2 cos of Q1. Cos of Q1 is 1, and Q2 is half, so it is 1 over 2, and sine of Q1 is 0. So we get this Jacobian matrix. And the moment you change any, let's say Q1 is theta, Q1 is 90 degrees. And let's say Q2 is the same. Then your arm will point upward. It will be pointing upward so that your Q1 is 90 degrees. So now your velocity part of the Jacobian will be minus Q2, sine of Q1 will be, sine of 90 will be 1, so you will get minus 1 over 2. And cos of Q1, cos of 90 is 0. And Q2 cos of Q1, Q cos of 90 is 0. And sine of Q1, sine of 90 is 0. So now you will observe that the Jacobian matrix change. The values change. Here it was 0, 1, 1 over 2, 0. Now it is minus 1. Right? Similarly, if you keep on changing it, if you bring it here, and let's say your theta 1 becomes, Q1 becomes 135 degrees positive, because we are going this way, we are going counterclockwise. Then your Jacobian matrix will change. So the Jacobian matrix is a function of the, and not only Q1 will change in effect Jacobian, you can make Q2 also change. It's not, doesn't always have to be 1 over 2 meters. It could be more or less. Okay, so that is it. So we got the Jacobian matrix, and now we want to find the Jacobian, the part of the Jacobian which is related to the angular velocity. Okay, so I call it JO, but let's not call it JO. It's J omega. So just for the sake of making notation consistent, this one is J omega. Okay, so now how to find J omega? J omega, we have formula that is coming next, but here I'll do it directly by just looking at the arm. Okay, so okay, now where is the diagram? Here. Okay, so we know that the only motion that the end effector, that the tool frame can undergo through, is the change in the angular velocity, angular position about Z0. And that's just because this is the only joint contributing to the angular motion of this, and that is only about, that's only possible when omega is equal to Q1 dot. Okay, so that's why I'll just put 1 here, because I already know that omega is equal to Q1 dot. So when I multiply this, omega will come out as Q1 dot. Q2 dot is linear motion. It's not contributing to the angular motion of the end effector. So this part is pretty straightforward. J1 is 1 and J2 is 0. First column, second. In fact, this should be J31 and this should be J32, because the previous 2 rows we already found above. Okay, so bringing everything together, our Jacobian will look like this. And you will wonder, where is Z0? So Z0 is always 0. This joint cannot achieve a motion about Z, and a motion along Z. And this is apparently omega Z, omega X, and omega Y are 0. Okay, So if you want, you can also write this. If you want, you can also write this Jacobian as okay. You can also write it as this: J11, J12, and J21, J22, and then we know that there is 0, 0, 0, and J61, J62. The reason I'm doing that is I told you that this vector will always be 6 by 1. So it will be x dot, y dot, z dot, omega about x, omega about y, omega about z. And the reason I put 0, 0 here is when you are finding omega about z, about x, you just multiply 0 with q1 dot and this 0 with, you multiply this row with that column, which will give you omega x0. And omega y, I know it will always be 0. And omega z is jx1, which will be what? Which will be 0 and 1 and 0. But the reason I'm not writing the Jacobian like this is I know that because of the geometry of the arm, this motion is never possible. So why to write it in the velocity vector? So we just write 3 velocity, we just don't write 6 velocity. You can write 6 velocities, but you just have to have those 3 0 rows, which it doesn't make any sense. But if you have, let's say, 6 joints here, these elements will also be non-zero. So generally Jacobian is 6 by n. Okay, n here is 2. And then we did this numerical where q1 is given to be 0, q2 is 1.2, 1 over 2.5 meters. q1 is rotating with a 2 radians per second, positive, counterclockwise. And q2 dot, the velocity, linear velocity of the second joint is 1 meter per second. And I just ask you to find the Jacobian, and then you just have to plug in these values in here. So you get this Jacobian, 0, 1, 0.5, 0, 1, 0. If you do not want to write it in the matrix vector form, you can just do multiplication. X dot is 0 times q1 dot plus q2 dot. So x dot is q2 dot. And we know that because q2 is a linear velocity. So that's why it's contributing to the linear velocity part, Vx of being the tool frame. And that's 1 meter per second. And similarly, y dot is coming from half of q1 dot. And q1 dot is theta dot, and this is your r. Is this your, think of this your r. So 0.5 multiplied by q1 double dot, q1 dot is 2 radian per second, it will give you 1 meter per second as well. That's a tangential velocity, you can say. That's a y component of the velocity of the end effector. And from these two, I can find the resultant velocity, which is Vx squared plus Vy squared, which is under root 2, square root 2 meters per second. And then I can also give tell you what this theta is, what theta this V makes with the x-axis, global x-axis. That's the inverse tangent of the Vx over Vy. That's 45 degrees because Vx is 1, Vy is 1. When both the xy components are 1, we know that the resultant vector makes up 45 degrees because the slope is 1 and tangent inverse of 1 is 45 degrees. The angle is 45. So, and how do you find omega? Omega is 1 times q1 dot plus 0 times q2 dot. You get q1 dot. q1 dot is 2 radians per second. It was given. So that's your angular velocity. So this was a numerical question. And they found it here. If you don't have a And in my case, on the previous slide, this I call this Vx, and I call this Vy. Okay. Any questions so far before I move on to the next topic? Now, I mean, just continue the topic. The same topic, but I'll proceed only if you don't have any question. No question? ठीक है. Acha. Next is, if you look at this, you were given joint velocities and you were to find the effective velocity. But practically, just think about this in an industrial application of robots. You wouldn't have these velocities. Let's say you want this to paint on a wall. The indefector is having a brush, holding a brush, you want to paint along the wall. So what you do is, let's say you want to move along X dot, along the Y direction, sorry, and then you want to move along the wall with a constant velocity of, let's say, 1 meter per second. So you want the arm to move with a constant velocity upwards, because let's say the wall is here. Or you can do welding, you can do cutting, you can do spraying, you can think of a lot of applications. You just want the arm to move, let's say, from one point to another point in a straight line, from one point to another point in a curved line. So you plan the motion here, and then you find the corresponding joint velocities. This is the inverse of what we did here. What we did here was a forward kinematics problem. We knew this, they were given, and we found these. But in practical application, we'll be given this, and then we have to go and find this. In order to find, given these, and in order to find these, we have to take the inverse of this matrix and multiply with these velocities. Only then we'll be able to find Q1 dot and Q2 dot. That will be inverse differential velocity problem, the Jacobian inverse. So that's what you see here. In order to find Q dot, you have to multiply. So think of this as this. In order, you have this velocity vector, you have this Jacobian, and you have it's multiplied with this. You want to get rid of this guy. You want to multiply both sides by the inverse of the J. So these will give you identity matrix. So which means you have Q dot here. This will give you identity matrix. And on the left side, you have J inverse multiplied by V. Okay, so this is the inverse of the Jacobian. So let's do it. How we take the inverse of this matrix. So before we do that, I want to remind you how you take the inverse of a 2 by 2 matrix. It's 1 over determinant multiplied by the adjoint of that matrix. So in case of a 2 by 2, it's very straightforward. The determinant is just A times D minus B times C. You just multiply the diagonal elements and find the difference of it. And the adjoint is, if you recall, you would exchange the positions of these two elements. You make AD and DA, and you change the sign of these two. This was the shortcut that we just remember. The actual formula was, what was the actual formula? There was -1 raised to the power I plus j. Okay, remember that. So I will go that into the details in the next class, but right now let's use just this formula. Okay. So we need to first find the determinant. So the determinant will be minus Q2 sine of Q1 multiplied by sine of Q1 minus Q2 cos of Q1 multiplied by cos of Q1. So that would give me minus Q2 sine squared of Q1 minus Q2 cos square of Q1. So take Q2 common, minus Q2 common, and then you get sine square Q1 plus cos squared Q1, which is 1. So we get minus Q2. Okay? And this is very important, this determinant. What happens when the determinant becomes 0? Anyone? What happens to the inverse of a matrix when the determinant of that matrix is 0?
Not exist. Singular matrix or not singular concept आता है.
तेज बोले मुसव्विर.
सर फिर हम इनवर्स नहीं फाइंड कर सकते क्योंकि सर डिटरमिनेंट अगर 0 हो जाता है सर हमारे पास नॉन सिंगुलर मैट्रिक्स आ जाता है सर.
Exactly. तो हमारे पास जब ये 0 हो जाए तो the inverse does not exist. Okay? So इधर अगर आप देखें तो determinant is depending on the value of Q2. इसका मतलब ये है कि अगर आपने Q2 का ये जो डिस्टेंस है ये 0 कर दिया तो फिर आप जैकोबियन का इनवर्स फाइंड नहीं कर सकते, और जब जैकोबियन का इनवर्स नहीं फाइंड कर सकते तो आप इन वेलोसिटीज के लिए ये दो वेलोसिटीज फाइंड नहीं कर सकते. द inverse differential kinematics problem is hard to solve. I mean, it's not giving you the solution. Okay? So let's consider this on the next slide. Okay, so here we are finding, so how to find the determinant? The determinant is just minus Q2. You saw it on the previous slide. And next is put sign of Q1 here and bring this guy here. Change their positions, and for the other two, exchange their position, and for the other two, change their sign. So you will get something like this. These two have changed their signs, and these two have changed their positions. And this is coming from here. So this is the inverse of the Jacobian. This is the inverse of the Jacobian. Okay? The example arm points in the x direction. X direction. Okay? It means this was your Z was, sorry, out of the page. And this is your x naught. Okay? And y naught is upward. Okay? And now what they want you to do is, with joint 2 extended to 0.25 meter, find the velocities to move the end effector such that Vx or x dot is 1 meter per second and y dot is 1 meter per second as well. So how to find it? Just plug in values here. This will be 1, this will be 1, this will be what? Anyone? Jacobian की value क्या
0.5.
यहाँ से शुरू करते हैं. -1/0.5 जिससे आ जाएगा -2. इससे आ जाएगा 1/-0.5 से आ जाएगा -2. अच्छा, ये क्या होगा? ये होगा sin of Q1. Q1 is 0 to 0. Minus cos of Q1. Q1 is 0, so minus cos is 1, -1. And minus Q2 cos of Q2 is -1/2. Cos of 0 is 1. And minus Q2, or ye 0 आएगा. We have to multiply this with 1 and 1. 1 meter per second, 1 meter per second. So कैसे होगा? It is just as you are multiplying this या 2 को उधर अंदर ले जाएं. So this will become +2 and this will become +1 and this will become 0. and then you multiply with 1 and 1, and then you get 2 plus 2 plus 9, 2 plus 9, 2. This row, this column. So then it will just give you 2, and the bottom one will give you 1. ये किस चीज़ की वैल्यूज हैं? ये Q1 डॉट की और Q2 डॉट की. यूनिट्स क्या है? ऊपर वाला रेडियंस पर सेकंड और नीचे वाला मीटर्स या मीटर पर सेकंड. सो Q1 डॉट इज 2 रेडियंस पर सेकंड, Q2 डॉट इज 1 मीटर पर सेकंड. सर Q1 की वैल्यू 0 किस तरह आई? तो Q1 सईदुल्लाह देखें ना इधर, Q1 की वैल्यू 0 है क्योंकि ये हम कह रहे हैं कि भाई अच्छा, if this is your Z0, ठीक है, if it is your Z1, so where is your X1? Your X1 is upward और Y किधर है? Y will be out of, Y1 will be out of the plane. ठीक है, तो Q1 की वैल्यू 0 इसलिए है कि इधर देखें, इस if you look at, if these are your two X and Y coordinates, let's say X and Y, and I have this link. So what do you think the value of theta is? It's along x-axis, so what is the theta? 0. But if it moves upward, what is the theta now? 45 degrees. If it is along y-axis, what is the theta now? 90. 90 plus 41, 135. 180. 275 and so on. ठीक है, तो इधर आर्म को देखें ना, ये आर्म इसी तरह पड़ा हुआ है ना ये, तो that's why Q1 is 0. लेकिन आपके लिए Q1 की वैल्यू कुछ और भी हो सकती है. इस वक्त तो हमारा Q1 ही आर्म ही इस तरह पड़ा हुआ है. ठीक है, so this is what, does it answer your question, Sayyidullah? Okay, so this is why our Q1 is 0.
ओके सर.
हाँ जी, लेकिन याद रखें Q1 0 है, Q1 डॉट 0 नहीं है, क्योंकि हम तो एक लीनियर एंगुलर वेलोसिटी के साथ वी आर मूविंग. अब आप कह रहे हैं कि जब हम मूव करने लगेगा तो Q1 तो फिर चेंज होगा, तो हाँ चेंज होगा ना, तो जैसे ही चेंज होगा उधर उसकी वैल्यू भी चेंज होगी जैकोबियन के एलिमेंट्स की. तो इसीलिए आई वांट टू शो यू, अगर मेरे पास इधर है इंडस्ट्रियल रोबोटिक, ये, so let me show you the Jacobian की ये किस तरह चेंज होता है. इसकी जब आर्म को मूव करते हैं तो how the values change. So let's say we have this robot, ठीक है, and let's set the environment to white, and let's look at the forward kinematics and inverse kinematics. So this is the Jacobian part, this one. अब इसमें 6 values क्यों है? I mean 6 rows क्यों है? क्योंकि 6 velocities हमारी है, Vx, Vy, Vz और Wx, Wy, Wz. ठीक है, और कॉलम 6 क्यों है? क्योंकि 6 जॉइंट्स है इसमें. तो अब आप देखें, जब मैं आर्म को मूव करता हूं, एक भी थीटा चेंज करता हूं, तो जैकोबियन के वैल्यूज देखें. ठीक है, सेकंड जॉइंट देखें ये, ठीक है, अच्छा, इसमें थोड़ी सी करेक्शन कर दूं, इस डायग्राम में ये Vx है, ये Vy है, ये Vz है, लीनियर वेलोसिटी। ये ओमेगा अबाउट x है, ये ओमेगा अबाउट y है, ये ओमेगा अबाउट z है। ये जिसने ये सिमुलेशन डेवलप किया उसने ये गड़बड़ की है। वरना नॉर्मली ये 3 रोज ऊपर होने चाहिए और वो 3 रोज नीचे होने चाहिए। ठीक है, सो द जैकोबियन चेंजेस। अब सिर्फ ये नहीं, अगर मैं इसको कोई पाथ दे दूं, ट्रेजेक्ट्री, जॉइंट ट्रेजेक्ट्री, तो अब देखें इसको, स्लो करें जरा इसको ना। अब देखेंगे जब आर्म जैसी मूव होता है तो उधर जैकोबियन हर पॉइंट पे चेंज होता है। ठीक है, so if you look at this, so this is what the Jacobian matrix looks like. I'll stop the recording because